So let's begin and let's go slowly because in module 2, not much things are there, not many things are there. So I've already discussed the bivariate distribution in terms of probability, joint probability mass function. And also I discussed a joint distribution function corresponding to discrete bivariate random variables. So that thing is okay, has already been done. And my today's discussion is about bivariate distribution or continuous case. Although I have written multivariate distribution, but you know bivariate is a special type of multivariate distribution. When the number of variable is more than one, then we call them multivariate distribution. Bivariate is a special type where the number of variables present is 2. I shall go very slowly in today's class because this thing is, as you can see in front of you, I'm moving my cursor. You see this expression, I don't know whether you know this expression or not. A little bit, maybe it is unknown to you. I don't know. What is your opinion about this expression? So far as I can say, yeah, you probably, since you belong to EC department, probably you have done double integration in your first year syllabus. So you know what double integration is. Okay, you know it. CSE students and IT students, they do not know. Anyways, so we shall be using problems corresponding to this notation. And remember one thing, before I start my today's session, I must say that this chapter, which is giving you the idea of bivariate probability density function or joint probability density function for bivariate variables, this is just a mere generalization of univariate variables. Okay, so here I shall be discussing problems of which are a little bit of mathematical or analytical type of problems, but I shall not be able to give you some application, real life application corresponding to this chapter. I have not yet found out such problems. I have looked for such problems in the book, and none of the books have discussed the problems of application oriented problems. Okay, just like we used to do in probability class. I have not found yet. Okay, so I shall be discussing a pure mathematical problem in today's class. Now, let us start. My first definition goes like this: a bivariate function with values f of x comma y defined over xy plane is called a joint probability density function of the continuous random variables capital X and capital Y, if and only if. Now you see what is written. These notations are very, what shall I say? These are very confusing notations. So whenever you write something or do calculations, you just be careful about the notations. What is it? What is it saying actually? Probability, and under this bracket it is written the ordered pair capital X and capital Y. It's not small x and small y. Capital X and capital Y belonging to some set capital A. Probability of that will be calculated using the formula, using the integration, double integration over the set capital A of the function f of x comma y with respect to x and with respect to y. That is what we denote by probability of capital X comma y belonging to A. Now, what is this A? A is any region on the XY plane. Okay. Now, we shall come to that point. We shall come to know about what the region here is. So we'll discuss this with respect to a problem. Okay. So let's move on to the next theorem, and then I shall again come back to this definition. Now just look into the definition, and if you have copies in front of you, you just write this expression, because I shall be scrolling down and you'll be missing this point. Okay, so you just write this expression on your copy so that you can correlate the problem with the expression. Okay, you can refer this particular expression while solving the problems. Now my next theorem is, I have saved the chat. Okay, my next theorem is what it says. Let us read it. A bivariate function can serve as a joint probability density function of a pair of continuous random variables capital X and capital Y if its values f of x comma y satisfies the following condition. Now you think about the univariate case. In univariate case, we first of all we learned about discrete probability mass function, and then we learned about a continuous case where we discussed about probability density function. And after that, what we did, we studied the properties of the probability density function. And for univariate case, we know if we represent the probability of the random variable by fx, we know that each fx, the fx is non-negative for all possible values of x. And also, if we integrate fx from minus infinity to plus infinity, that is over the entire real line, that area is 1, that is, it has unit probability, or sum total probability is equal to 1. This expression, okay, marked pink, is just a generalization of that univariate case. It's about bivariate case, and it is said that if we have a bivariate function like f of x comma y, for each pair of variables x and y lying in the real line, x lying from minus infinity to plus infinity, and at the same time y lying between minus infinity and plus infinity, fxy for each possible values of x and y will be non-negative. And since here we are discussing about function of two variables, then we must have the double integration over the function f of x comma y with respect to x and y integrating from minus infinity to plus infinity for both y and x will be equals to y. The first integration, these limits are for y, and the second integration represents the limits for the variable x. Okay, so this result is just a mere generalization of the result we discussed in the univariate case. It is nothing new, but the way we shall be applying that in the problem, that is new. Okay, so you just concentrate on what I say in my next discussion. We will be discussing this particular problem. I hope that you have copied this particular formula in your copy. Okay, so I'm scrolling down. We don't need this. For discussing problem, we don't need this. Okay, this is just a property. Now, what is the problem? The problem says, given the joint probability density function, now the fxy is given. Okay, a form of f of xy is given, which is 3 by 5 x into y plus x. X is lying between 0 and 1. Y is lying between 0 and 2. And f of xy has value 0 elsewhere. Means when x is less than 0 or x is greater than 1, even if y lies between 0 and 2, probability is 0. If y less than 0 or if y greater than 2, even if x lies between 0 and 1, then fxy is 0. If both x and y less than 0, or if both x and y greater than 1 and 2 respectively, result is 0. So this function is only valid when x lies between 0 and 1, y lies between 0 and 2. I hope you have understood. We are supposed to find the probability that capital X comma Y, this pair of random variable, takes values from a region which is denoted by capital A. What is that region? The region capital A has been defined here. You see, it is the set of all two-dimensional points on the XY plane. Capital A represents all the represents a collection of all the points on the two-dimensional plane of the form x comma y, where x lies between 0 and half, y lies between 1 and 2. And you see that for the interval in which x lies, that is 0 half, is a sub-interval for 0 1. And the interval in which y lies, 1 2, is a sub-interval for 0 2. So we are actually going to calculate the probability that capital XY belonging to A in these sub-intervals, okay, for x and y. So this is the meaning of the expression. I have explained what these expressions mean to you. Okay, the understanding of this expression is very important before you start solving problems. Now, Let us solve this problem. Now, probably since you know double integration, I hope that so far as I can remember, EC students know double integration. So even since this, I'm going to discuss this probability, finding of this probability over here. Let me discuss a little bit of about double integration over here. Now I have drawn this diagram. Okay, so this diagram here, suppose this represents x-axis and this represents y variable. And suppose that this is my range from 0 to half for x, and this is my range from 1 to 2. Sorry, this is my range from 0 to 1 for x, and this is for 0 to 2 y. Now, if I join them, if I drop perpendicular from here and from here, and if I intersect them here, then we get a kind of rectangular region on the xy plane. Now double integration means, and see, if you plot this particular function, if we plot this particular function, that means this function, that means what? We are going to erect something where the base will be represented by 0, x lying between 0 and 1 and y lying between 0 and 2. The base is represented by this. Okay. Now, what is double integration? Double integration means, first of all, we are going to integrate from 0 to 1 for x. So we are going to integrate with respect to x first. Okay. So that means 0 to 1 for x, 0 to 1, 0 to 1, 0 to 1. Imagine as if I'm drawing some kind of lines over here. 0 to 1, 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 as many 0 to 1 as I can consider. So some lines drawn parallel to this line of this part of x-axis has been drawn. Imagine, just imagine. And then we are going to integrate from 0 to 2. So let us draw the lines like this: 0 to 2, 0 to 2, 0 to 2, 0 to 2, 0 to 2. So we get what? We get a kind of thing like this. We get a kind of thing like this, a scroll, some set of lines intersecting with some lines like this. We're going things like this. Okay, probably you are understanding what I mean to say. Okay, we're going thing like this. Okay, where we are going this kind of things on this base. Where we are going this kind of things on this base. So this base is actually represented by this. What we are actually calculating? We are calculating the area of this particular base on which the function will be erected. Okay, that is how we try to represent the calculation of double integral. We calculate the area of the base on which the function will be erected. I don't know whether function will be what will be the shape of this function. If you can if we can plot it, then only we can see its actual shape. But by double integration, I'm just explaining to you what double integration is. So we are actually calculating the base, the area of the base of this particular function. Now, what we are supposed to find over here, that was the explanation of double integration. What we are supposed to find over here? We are supposed to find that what is the probability that the random pair of random variables capital X comma Y will take values from this region A, which is the base of this, which is represented by this base. Okay, how to calculate this? My objective is to deal with the probability. I'm not here to teach you double integration. First of all, we are, according to the definition, we are going to integrate with respect to x. And since x limit is this 0 to half, so we are going to integrate from 0 to half. So x has been taken limits from 0 to half, and my function is this one, because 0 to half is the sub interval of 0 to 1. So this function is valid over here. We are going to integrate this function. We are going to integrate this function with respect to x first and put the limits. And since we are going to integrate this function with respect to x first, then if the variable y present over here will be treated constant. The variable present in this case will be treated constant. Okay. So how will I proceed? You first see that the constant 3/5 has been taken outside the integration sign. Okay. And inside we have integrated. Y remaining constant, we get y into x square by 2 plus x cube by 3. limits of x have been put from 0 to half. And if I put these limits, I will get an expression like this: y by 8 plus 1 by 24. In between steps have not been shown. Okay, so you just verify that it is coming. So this is the function now. This is the integrand now. And this integrand is the function of y. What is the function here? Y by 8 plus 1 by 24. That is the function. We are going to integrate this function with respect to y now. And putting the values limits from y equals to 1 to y equals to 2, we ultimately get 11 by 80. So what does it do? What we have calculated? We have calculated that 11 by 80 is the probability by which the pair of random variable capital X comma Y will take values from the region which is represented by this base. So that probability has been calculated over here. I hope that you are able to understand what I mean to say over here. Otherwise, when I shall be uploading this video in YouTube and I'll be sharing with you, then you go through my videos once again and follow this particular section of the lecture again and again. You will definitely understand. Okay. Even if you find difficulties, then I'm there. You can anytime ask me in the class, after the class, okay, or sometime later, whenever you think it's feasible. My next definition is about this. So when we studied probability density function or probability mass function for discrete case, for univariate examples, we calculated immediately after that we talked about distribution function, which is sometimes called cumulative distribution. Also, if you see my last lecture in YouTube, you will find that I have discussed this distribution function in terms of discrete random variable for bivariate case. So naturally, I need to generalize the thing for bivariate examples in case of continuous variables. So here is the definition. The definition says, if capital X comma Y are continuous random variables, the function given below, the same old form, capital F of X comma Y, probability, this means probability that capital X will take values lesser than or equal to X, capital Y will take values lesser than or equal to Y, jointly. So this is called the joint probability. And this means, if I write it in terms of integration, it means that integration from Y ranges from minus infinity to Y, and X ranges from minus infinity to X. And we have introduced two new set of pair of variables which will take positions of X and Y respectively. So S is taking the part of X and T is taking the part of Y. We are going to first integrate with respect to ds, with respect to S, and then the function will be integrated with respect to T. So you all, I ask all of you to write this expression in your copy, okay, because I'm going to scroll down. And as usual, these x's and y's will lie on entire real line, okay, x on x-axis and y on y-axis jointly, where FST is the joint probability density of x and y at ST is called the joint distribution function. Joint distribution function FST has already been defined above. Okay, we have already discussed about FST in a few minutes ago. So that is, given FST, we are going to find the distribution function in case of bivariate variable continuous nature. So here is a problem. Problem is, if the joint probability density of capital X and capital Y is given, now this is joint probability density function is given here. F of xy is x plus y when x lies between 0 and 1 and y lies between 0 and 1 and 0 elsewhere. Find the joint distribution function of these two random variables, capital X and capital Y. Now, what did I say? I would not be able to talk about real life applications. Now you see, I am discussing problems. I'm telling you to how to calculate the probabilities, but the questions which I am taking, these are purely mathematical questions. What is the base of this function? From where does this function come? From which real life situation it has come? I don't know. Okay, and I have not got any such problems which I can discuss. If I get, I shall definitely discuss with you. I'm still looking for that kind of problems. So let us discuss this. And this problem is very important, so you be attentive and listen to me very carefully. It's a very little bit, a bit complicated. Not complicated, but if you are not lost in a myriad of what should I, notations, then this problem is nothing. And if you are lost in the this huge wave of notations, then this means something to you. How to calculate this type of problem? Okay, the joint probability density is undefined. We shall try to derive different regions to calculate the joint probability. Okay, we shall try to divide this region in different parts. First of all, we are going to take that this x and y, they are both less than 0, negative. And if x is less than 0 and y is less than 0, so you see f of 0, 0 will be probability of x less than 0, comma y less than 0 jointly, which will be small f 0, 0, which is 0, because it is written elsewhere. Okay, now I'm showing you 4 regions over here. What are these regions? What do they represent? How the regions represent themselves? Okay, the above region is divided into 4 parts. Okay, since x is lying between 0 and 1 and y is lying between 0 and 1, so positive quadrant has been chosen. Now, if x is lying between 0 and 1 and y is lying between 0 and 1, this means this is your region 1. When x is greater than 1, x is greater than 1, and y is lying between 0 and 1, that is your region 2. When x is lying between 0 and 1, when x is lying between 0 and 1 and y is greater than 1, that is your region 3. And when x is greater than 1 and y is greater than 1, that is your region 4. Okay? Once the region has been divided, we are going to calculate this joint distribution function separately for each region. So my first case is region 1. Listen to me very, very carefully. This is my region 1. F of x comma y. How to calculate? First of all, we are going to integrate from 0 to y. Okay, in region 1, you see x will lie between 0 and 1 and y will lie between 0 and 1. Now, if you put 0 to 1 and 0 to 1, total probability will be 1. Okay, so you will not get any kind of function form for the distribution. So here I have made the upper limit variable. Y is something which is less than 1 and x is something which is less than 1. Now we are putting the value, the expression of the function f of st. Now what is f of st? F of x, y is x plus y. So f of st will be s plus t. Okay, and we are integrating as before. Okay, putting the limits of x from 0 to x, and we are getting this some expression which has been integrated with respect to t, and putting the limits y, we have got this expression. You verify this integration, do the calculation by yourself and to check whether it is coming or not. Okay, region 2, I have shown this region elaborately, so you pay attention. F of x, y, now here capital X is less than or equal to, now capital X is less than or equal to small x, but here the nature of the small x is x will be having values greater than 1. This is the nature of small x. Y is less than or equal to small y. What is the nature of small y? Nature of small y is y will lie between 0 and 1. So inside this first parenthesis, the nature of these variables x and the nature of the variable y has been written. Don't get confused. Now, I have put the limits from minus infinity to y, minus infinity to x. By definition, this is my definition of f of x comma y, fst ds dt. Now this this limit, you see, this limit has been divided into 2 halves. The outer limit is minus infinity to y, has been divided into two halves. One is minus infinity to 0 and another will be 0 to y. Now in this region from minus infinity to 0, the integrand will be 0. Whatever you put, that will be 0 because of the definition of the function. That thing will vanish. Here we are left with only this portion. Integration 0 to y, integration minus infinity to x, fst ds dt. Now this inside limit, the inner limit, has been divided again into two halves with respect to x. So the limit of x is changing in this manner, minus infinity to 0 and 0 to 1. Okay, so minus infinity to 0 gives you what? 0. The functional value over in this region is 0. So we are left with 0 to 1 part only. So we get ultimately 0 to y, 0 to 1, and function's form is s plus t ds dt. Okay, is equal to, when we integrate that, you integrate this portion, you fill in the blanks, you integrate this portion, you will find that the expression will come out as half into y plus 1. Okay, so two parts have been calculated. One part is this and another part is that. Region 3, similarly we see f of x comma y is probability of x less than or equal to, here the nature of x is lying between 0 and 1, and nature of y is greater than 1. So just like my previous example, I have divided the limit of y into two halves, from minus infinity to 0 and 0 to 1. This part will vanish according to my previous logic or reasoning. That part will remain. The inner limit has been divided into two halves with respect to x, from minus infinity to 0 and from 0 to 1 and 0 to x. I am keeping these limits as y and x because otherwise if you put some definite values for x and y in the upper limit, remember some concrete value will come out of the calculation. But we do not need the concrete value, we need a functional form, because we are actually not calculating the probability, we are calculating the distribution function, and that function should be in terms of x and y. So that's why we are writing here y and x. And we know that y will bear this particular rule and x will satisfy that particular rule. Keeping this in mind, we are dividing the region into halves. So ultimately from this expression, we are going to get integration 0 to 1, integration 0 to x, s plus t ds dt, and that will yield half x into x plus 1. And lastly, for region 4, we did the same thing, f of x comma y, probability of x less than or equal to, here nature of x is x greater than 1 and nature of y is y greater than 1. And similarly, with similar logic, we have divided these into two halves, one half getting vanished. Inner limit again is divided into two halves with respect to t or x. And ultimately we are going to calculate this as 1, because that has to be, because when x greater than 1 and y greater than 1, you know distribution function is or we know it as cumulative distribution is just like cumulative frequency. Try to recall, what did I say? The last value of the cumulative frequency is exactly equal to the total frequency. So here the last value of the cumulative frequency or cumulative distribution, that is this one, should be equal to the total probability, and total probability, you know, total probability is always 1. So when I get this, that means my logic, my calculation is all right, because it is satisfying the rule. And since the joint distribution function is everywhere continuous, the boundaries between any two of these regions can be included in either one. We can, by combining all the regions 1, 2, 3, 4 together, we can write the entire thing in this particular manner. This is my distribution function which I have calculated. So f of xy has become 0 when x less than or equal to 0, y less than or equal to 0. It has become half xy into x plus y when 0 less than x less than 1 and y less than greater than 0 and less than 1. It becomes half into y plus 1 when x is greater than or equal to 1 and y lying between 0 and 1. It becomes half into x plus 1 when x is lying between 0 and 1 and y is greater than 1. And this becomes 1 when x is greater than or equal to 1 and y is greater than or equal to 1. Remember one thing, in continuous probability, if you write that, suppose in univariate case, if you write probability of 0 less than x less than 1, that will be same as if we write probability of 0 less than or equal to x less than or equal to 1. That will be same as if we write probability of 0 less than or equal to x less than 1. That will be same as probability of 0 less than x less than or equal to 1. So equality sign is actually not impacting the entire calculation. If I take a bucket of water from ocean and put it aside, the ocean remains the ocean. Its nature doesn't change. So including equality, or if I pour some 2 buckets of water, say, or 1 bucket of water in the ocean, the amount doesn't remains unchanged. Changed, definitely changed, but so negligible that it is not caught by the eye. Okay, humanly not possible. So here, if we include the limits or if we exclude the limits, since we're dealing with continuous cases, this exclusion of boundary limits or inclusion of boundary limits doesn't at all affect my entire calculation. So don't get confused that here I am written y greater than or equal to 1 and here I am also writing y greater than or equal to 1. If you are confused, I will suggest that, okay, this is printing mistake, you make it y greater than 1. But if you do this kind of mistake, this is not a grave issue. Okay, for continuous case, but discrete case, it becomes a grave issue. So you have to distinguish between continuous and discrete case. Their natures are a little bit of different. I have given a problem here. If the joint probability density function is given like this problem is similar to the problem discussed in the beginning, the first problem. We are going to calculate the probability this, and this. Okay, so my time is already almost running out. I have calculated one probability for you. Probability of x less than or equal to half, y less than or equal to half. The condition is x comma y greater than 0 and x plus y less than 1. This implies that x must be lying between 0 and 1 and y must be lying between 0 and 1. Okay, so the rest is to calculate this probability, and 0 to x lying between x is less than half means what? Means we are going to integrate from minus infinity to half with respect to y and from minus infinity to half with respect to x. We are going to divide the region of x into 2 halves, minus infinity to 0 and 0 to half. This portion will vanish. And 0 to half, that portion, 0 half, this interval is a sub-interval of 0, 1. So the functional form will be valid in this region also. The functional form is 2. The function is given as 2. You see? This is my function. Okay, and therefore f of st will be 2. So I have put the value of the function, integrated it. We got integration minus infinity half dt, and then we are dividing the outer limit y into 2 halves from minus infinity to 0 and 0 to half. This vanishes, and ultimately we get the probability as half. So I have solved this problem for you. The second 2 problems, the remaining 2 problems have been kept for your practice. Try to solve the remaining 2 problems by yourself. Probability that capital X plus Y greater than 2 by 3 and probability that X greater than 2Y. Okay, try to solve these 2 problems. This is your homework today. So before I conclude my today's class, I must ask all of you, those who are listening to me carefully, that if we were practicing problems from module 1, put it aside. Now for this week, we just concentrate on module 2 and module 3. No questions will be set in the continuous evaluation test from module 1 and nothing related to module 1. Everything will be on the basis of the contents of module 2 and module 3. Okay, so you just concentrate on that. And the total number marks in the examination will be 25. 12 into 2 is 24. So there will be 12 MCQ type of questions of 2 marks each, and one question will be of 1 mark. So thus will be getting 25. And the question will be asked, the exam will be taken through Google Classroom. And I hope that your performance in this examination will also be similar to your performance in quiz test. So you don't have to worry much, but you just study. And tentative date for the examination is 7th of September. That is next Monday. I shall inform you. I have not prepared the question yet, but I shall inform. The dates may vary a little bit. Okay, but you keep in mind that your tentative date till today is 7th, and accordingly you proceed. I have saved your chat. Okay, so thanks to God that my internet connection remained stable throughout the session, and I hope that you have understood what I discussed today. Bye for today, and we'll meet again on day after tomorrow. Till then, bye bye.
Thank you, sir.
Yeah. Okay.
Thank you, sir.
Thank you, sir.